Hello everyone, welcome to this lecture on predicate logic. Just to recap, till now we had extensively discussed about propositional logic, how do we form compound propositions, how do we verify whether argument forms are valid, various ways of verifying argument forms are valid or not using rules of inferences and so on. The plan for this lecture is as follows. In this lecture we will discuss about predicate logic and its motivation. We will discuss about quantification mechanisms and we will discuss about logical equivalence in predicate logic. So, let us start with the motivation of studying predicate logic. So, it turns out that even though propositional logic is very interesting, it cannot represent all kinds of mathematical statements that we are interested in. So, for instance, consider this declarative statement that x is greater than 3, which is a declarative statement, but it is not a proposition because until and unless the value of x is assigned, we can't decide whether this statement is true or false. Whereas, the definition of proposition is it is a declarative statement for which we know that it is either true or false, but not simultaneously it cannot take the value true as well as false. So, that is not happening for statements of this form. So, the question is how exactly we can represent statements of this form, because in general when we are writing mathematical statements, we are very often we want to characterize properties about arbitrary sets, arbitrary domain, where without worrying about the underlying values which are going to be taken in the domain and so on. Okay. So, for that we need predicate logic. So, it turns out that there are two parts of the above statement which we are interested to represent. The first part is the variable x, which is the subject of the statement, because in this statement we are trying to say something about the property of x. We want to say that okay, x is some value which is greater than 3. We do not know whether that is true or not, because that depends upon the exact value that x is going to take, but we want to characterize the property that whatever is the value of x, it is greater than 3 or not. So, greater than 3 is the property for the subject x. So, the way we represent these statements, this statement in the predicate logic is we introduce a function which I call as a predicate function, and this predicate function typically they are represented by capital letters. Okay. So, they are represented by capital letters and the choice of exact capital letter is up to you. You can use M, A, B, C, anything. And why we are using capital letters? To distinguish it, differentiate it from propositional variables for which we use lower cap letters. So, the propositional variables they are represented by lower cap letters, predicate function variables they are represented by capital letters. So, this is a function of a variable x, okay, where x can take any value, and this p of x becomes a proposition when we assign a concrete value to x. Okay. So, for instance, if I assign the value 4 to x, then the proposition that I obtain is p 1, which is 4 is greater than 3. Now, the statement 4 is greater than 3 is indeed a proposition. It is a declarative statement and we know it is a true statement. That means, there is no ambiguity about the truth value or the truth status of p 1. Whereas, p of 3 is another proposition, say p of 2, which is the statement 3 is greater than 3. Now, this is a proposition because this is a declarative statement and the truth status of p 2 is confirmed here, it is a false statement. Okay, there is no more ambiguity left. So, now you can see that how we can represent or how we can deal with statements of this form, where we have some abstract variable and we want to state or declare some property about that variable using this predicate functions. Okay. It turns out that we can define multi-valued predicate functions, right. So, the previous example was for a statement where we had only one subject, namely the subject x, but you might be dealing with statements where you have multiple subjects. For example, we want to represent declarative statements of the form x equal to y plus 1 plus 3, right. So, this is not a proposition, because until and unless we do not assign values to x and y, we do not know what is the status of the resultant proposition. So, I can represent this statement by a predicate variable. I use the predicate variable capital P, and it is a function of two variables x and y. When I assign the value 4 to x and 0 to y, I get the proposition, say P 1, that 4 equal to 0 plus 1 plus 3, and this is a true statement, this is a true proposition. So, I will say that P of 4 comma 0 is true, whereas if I assign the value x equal to 3, y equal to 0, then this is a false proposition. Okay. So, now you can see that this proposition, this predicate variable, it is acting as an abstract function, a placeholder, and it can represent multiple propositions depending upon what exact values you assign to the corresponding variables which are there in the corresponding predicate function. Okay. In the same way, you can have 3 valued predicate functions. So, for example, if I want to represent x equal to y plus z, then I can introduce a predicate function p of 3 variables, and then depending upon the values which you assign to x, y, z, you get propositions which can be either true or false. So, now once we have predicates, we will be interested to convert them into propositions, because then only we can apply the rules of inferences, rules of mathematical logic, and do something meaningful with the resultant propositions. So, it turns out that there are 2 methods of converting your predicates into propositions. The method number 1 is you assign explicitly manually the values to your underlying variables, but it is very less interesting. We are not interested in this method, and this is what we were doing till now in all the examples that I have demonstrated. I have manually assigned the values to my underlying variables and convert the resultant predicates into propositions. We will be interested in method 2, which we call as the quantification method, because we will be interested to represent quantified statements of the form that something is true for all values in my domain, something is true for some values in my domain, something is not at all true for any of the values for my domain. Okay. So, we will be interested in these 3 forms of quantifications, and we will be discussing about various mechanisms, how to deal with such statements and so on. Okay. So, we will be first starting with 2 forms of quantifications, namely the universal quantification and existential quantification. What is a universal quantification? Well, whenever we want to assert that a property is true for all the elements of my domain, then I use universal quantification. So, very often you might have encountered this notation for all x in your theorem statements. You encounter this whenever we say okay, that some property is true for say all integers, all real numbers. So, very often we use this notation for all x, right, and say we want to say that all integers satisfy something something something, that something 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 is nothing but a predicate function. You want to say that some property p is true for all the x values in your underlying domain. If that is the case, then we use this notation. Okay. So, this expression for all x p of x is true if the property p holds for every value x in your domain. Okay. That means, for simplicity, assume your domain has m possible values of x. Well, your domain could be infinite as well. Say your domain could be the set of integers, that is possible, because you might want to assert a property which is true for all integers. But just for simplicity, I am assuming here that my domain consists of m number of elements, then the quantification for all x p of x is logically equivalent to conjunction of m propositions where proposition P of x1 denotes that proposition P is true the property P is true for x1, P of x2 denotes that property P is true for x2 and so on, and P of xm denotes that property P is true for x of m. Okay. That means, if this conjunction on your right hand side, if this is false, then for all x P of x is not true, that will be false. That means, even if you find one counter example, okay, or a bad witness, your counter example is nothing but a bad witness. Even if you find a bad witness, at least one bad witness for which the property P fails, I can conclude that for all x P of x is false. Okay. So, before proceeding further, I would like to stress here on the significance of the domain here. Whenever we are making quantified statements, it could be any form of quantification, it is very important that you clearly and explicitly say what is the domain of x. Say for instance, I make or I define a predicate P of x which says that x square is greater than 0. Okay, this is a predicate function which will be true if x square is greater than 0, it will be false if x square is not greater than 0. Now, suppose someone says that, is it the case that for all x P of x is true? Someone asks this question. How do you verify that? Well, it depends upon what exactly is the domain. If the domain does not include 0, that means you are considering a domain where x can take any value except 0, then yes, this statement for all x P of x is true, because the property P, namely x square greater than 0, will be true for every x except 0. But the same predicate P of x will not satisfy the condition for all x P of x. For all x P of x will be false if 0 is included in the domain. That means, your x can take the value 0. So, it is very important to explicitly mention what exactly is your domain. If you do not specify your domain, then universal quantification does not make very sense. The logical meaning will completely change as soon as you change the domain. That means, for the same P of x, for all x P of x may become true for one domain, but as soon as you change the domain, for all x P of x may become false. Okay. Now, let us go to the next form of quantification, which we call as existential quantification, and this quantification asserts that a property is true for at least one element of my domain. Okay. Here I am not interested to state that my property is true for every value in the domain. I want to stress that it is true for at least one value of the domain. Well, it might be true for every element of the domain, that I am not worried about. I am interested to assert that it is true for at least one element of my domain, and this is represented by this expression, there exists x. So, this notation stands for there exists. Okay. So, whenever the property P is true for at least or for some x in your domain, the expression there exists x P of x becomes true. Again, for simplicity, assume your domain consists of some m number of elements, then I can say that there exists x P of x is logically equivalent to disjunction of this m propositions, where first proposition is property P is true for x1, second proposition is property P is true for x2 and so on. That means, if your RHS is false, and when can RHS be false? When this disjunction is false. And when can this disjunction in your RHS will be false? When the property fails or the property does not hold for any of the x values. That means, P of x1 is false, P of x2 is false, and like that P of xm is false. That means, for none of the x values in your domain, the property P is true. In that case, the statement there exists x P of x will be false. But even if at least one of the x value satisfies the property P, then the statement there exists x P of x becomes true. Okay. Now, let us define what we call as bounded and free variables. So, a variable is called a bounded if there is a quantifier which is applied on it. So, for example, if I write an expression of this form, then x is bounded because x is there, because the quantification there exists is applicable on this x. But what about this y? This is acting as a free variable here. There is no quantification applicable on this variable y. Whereas, consider this expression, there exists x p of x disjunction for all x q of x. Now, so the question here is, am I talking about 1 x or am I talking about 2 x? It turns out there are two different variables, the two x's are represented by the same x here, which is the common source of confusion here. So, there are two different variables and two different quantifiers are applied on it. The there exist quantification is applicable on this x, which is the subject for predicate p, and the quantification for all is applicable on the second x variable, which is the subject for proposition q, right. So, what you can do is, to avoid confusion, you can either put explicitly the brackets to denote that okay, the there exists is applicable on p of x and for all is applicable on q of x, or it is recommended to use different variables if you do not want to put parenthesis to avoid confusion. Use different variables for different predicate functions if they are applied if they are applicable with respect to different quantifiers. Now, what is the scope of a quantifier? The scope of a quantifier is that part of the expression over which the quantifier is applicable. Okay. So, for instance, if I take this expression, this example, the scope of this quantifier is only limited to p of x. It is not limited to, it is not applicable to for all x q of x, no. In the same way, the quantification the scope of this for all x, the scope of this for all quantifier is applicable only to this q of x, it is not applicable to p of x. Okay. So, that means what is a free variable? A variable is free if it is outside the scope of every quantifier, right. So, if I take the first expression here, the scope of this there exist quantifier is this x, but if I take this variable y, it does not come within the scope of this there exist, because there is no quantification which is applicable over this y, and that is why this y is a free variable here. And if you have expressions involving predicate functions where you have free variables, then it is completely ambiguous, you cannot make any meaning out of that. Okay. So, now we can define logical equivalences even for the predicate world. We can define predicates, we can have quantified statements, and we can have two different expressions, and we can verify whether the two expressions are logically equivalent or not. So, for instance, if I want to verify whether the expression in your LHS part and the expression in your RHS part, they are logically equivalent or not, we can verify that. Okay. And see, I have explicitly used parenthesis here to distinguish the quantification of this for all x and this for all x. Okay. So, how do we prove logical equivalences involving predicate? Well, what was our definition of logical equivalence in the propositional world? If you have two compound propositions x and y, we said that x is logically equivalent to y if and only if x by implication y is a tautology. That was our definition of logical equivalence. That means x and y takes the same truth value, whenever x is true, y is true, whenever x is false, y is false. But now we are talking about arbitrary domains, arbitrary predicate functions, and so on. intuitively we will say that my expressions involving predicate functions are logically equivalent if they are equivalent with respect to any possible domain. Okay. That means it should not happen that the two expressions are equivalent for one domain, but there is some bad domain for which the two expressions are not equivalent. Even if there is one bad domain for which the two expressions are not equivalent, the overall expressions will not be considered as logically equivalent expressions. But now the problem here is that here in this particular case I am not specifying what is the domain of x, and I can't do that because whenever I am specifying logical equivalences involving predicates, my predicate could be over any possible arbitrary domain. Okay, because I want to state here that okay, this condition holds doesn't matter. So, the way you can interpret this statement is I want to prove that okay, my LHS and RHS are equivalent, it does not matter what is the domain of x. That is what is the meaning of logical equivalence in the predicate world. So, you might be wondering that okay, without even talking about the domain, how can I verify whether the LHS and RHS are true for every possible domain? The way we do it, we say that okay, we consider some arbitrary domain. That arbitrary domain could be the set of integers, it could be anything, and my property P, my property Q could be arbitrary properties. I am not explicitly specifying what are my properties P and Q. So, I am considering arbitrary domain and arbitrary predicates P and Q, and for simplicity I am taking a finite domain, but whatever I am saying here you can generalize it to infinite domains as well. Now, our goal will be to show that with respect to this arbitrary domain and arbitrary predicates P and Q, the LHS expression and RHS expression have the same truth value. If we do that, then that establishes the logical equivalence of this expression, because I am considering an arbitrary domain for which I am showing the equivalence here. So, let us start with the LHS part here. What is the LHS part? The LHS part says that for all x, conjunction of P of x and Q of x is true. Now, if remember for all x, P of x conjunction Q of x is true if the property P and Q is simultaneously true for every x value in your domain. That means this conjunction should be true. Now, what I do is I just shuffle the terms here. Okay. I bring all the P terms together and all the Q terms together. So, remember this P of x1, P of x2, all these are propositions. Okay. So, what I am saying is since for all x P of x and Q of x is true, that means P of x1 and Q of x1 is true, the proposition P of x2 and Q of x2 is true, and so on. And now, I am shuffling around the individual propositions. Now, if the conjunction of all the P propositions is true, that is equivalent to saying that for all x P of x is true, and the same way if the conjunction of all the Q propositions are true, that is equivalent to saying that for all x Q of x is true, and this is nothing but your RHS expression. Okay. In the same way we can prove De Morgan's law involving quantified statements. So, for instance, we can prove that if you have a negation symbol outside for all x, you can take the negation inside and there exist becomes for all become there exist, and you take the negation and put it before your predicate P of x. And a dual property will be if you have a negation before there exist, you can take the negation inside, there exist become for all, and property P is replaced by negation of property P. You can prove that using same thing. So, you can say that for all x P of x is equivalent to P of x1 and P of x2 and so on. That means negation of for all x P of x is nothing but negation of this entire conjunction and then you can apply the De Morgan's law of propositions, and you can take the negation inside each of them. So, and the conjunctions get converted into disjunctions. So, you get negation of p of x 1, disjunction negation of p of x 2, and so on. And since we want to assert that negation of p of x 1 is true, or negation of p of x 2 is true, and so on, that is equivalent to saying that the negation of p property is true for at least one value of x in my domain. Same thing you can do for second dual form of the De Morgan's law. Okay. So, that brings me to the end of this lecture. The references are for this lecture are the Rosen's book, and to summarize, in this lecture we started discussing about predicate logic. We saw the motivation of predicate logic, and we discussed how we can represent quantified statements. We saw two forms of quantifications, namely the universal quantification and existential quantification. Universal quantification is true when the property p is true for all the values in your domain. Existential quantification is true when the property is true for at least one value in your domain. And we saw some logical equivalence involving logical equivalences involving predicate involving statements having predicate functions. Thank you.